Section 6.4, first-order linear differential equations. A first-order linear differential equation is any equation of this form, where we have a derivative and we're adding some continuous function of x times y, and it equals another continuous function of x. So as long as it looks like this, everything we're about to do is going to work. So before we begin, it's important to understand you need to make the equation look like this standard form, okay? Again, where we have the derivative plus some function of x times our y, and that equals some function of x. If it doesn't look like this, this isn't going to work. Now, one of the reasons that we're going to have this special technique to solve this and why these are called first-order linear is because these aren't separable, right? We're not able to solve them the same way we did with some of our previous differential equations, but this gives you an idea as far as some real basic techniques of ones that aren't separable. There are many more, but in this class, we're going to stick with simply what are called first-order linear, which again looks like this in their standard form. Now, the general strategy is going to be this. We're going to basically choose a u of x, if you will, sort of like substitution, I guess. And we're going to make this choice of u where if we took u times p, the stuff right here, okay? So we want to multiply our choice of u times this p, but that relationship has to equal the derivative of u. Now, don't worry about trying to figure out what that's going to be. There's actually a method to this. But I want to show you why we want to do this. First off, if we go ahead and choose a u, right, that has this relationship, and we go ahead and put it in here, we can make a substitution. And this is how this is going to work. In our standard form, we have our, dy dx. And of course, right here, we have our, p of xy. And then over here, we have our q of x. So what I'm trying to say is that there's going to be a special value of u that we're going to choose. Okay, and I'm going to show you how to come up with it, where if you take u times p, it is equal to u's derivative. So let's just say we know what the u is. And again, we're going to come back to how we figure this out, but let's just say we know what the u is. If I know what that is, and I go ahead and multiply this u right in here, I'm going to be able to make that substitution. But of course, in the equation to maintain equality, if I multiply the u in there, I also have to multiply every other term in the equation by that. So I'm going to go ahead here and again multiply these by u of x. So as you can see, I've basically identified a u, which again we'll talk about, multiplied every single piece by it. So the magic happens right here. Because I know that u times p is equal to the derivative of u, I can substitute this part right here and replace it with the derivative of u. So let's go ahead and do that and see what it looks like, and maybe you'll understand where I'm going. So if I go ahead and write this part here, we're going to have our u of x, of course, times dy dx. Now, I'm going to, again, replace what I've underlined here with the derivative of u. And, of course, still multiplying that times y. And then over here, we just have the u of x times whatever q of x is. Now, here's why this is such a great idea and how it helps us solve. Now that I've replaced this part here with u prime, if you really focus on this whole side of the equation, what you'll notice is that this is actually the product rule. So if you think of two functions, one of them being u of x and the other being y, you can look at this as being the product rule between them. So if you look here, this is the derivative of y times u, plus this is the derivative of u times y. So clearly, you could rewrite this as being the product rule between y and u. And so if I do that, that means I can re-express this side to be the derivative of whatever u of x is times y. So it's kind of like working backwards, because again, this is literally the same thing as the product rule between those things, so I can rewrite it this way. That's why identifying a u with this relationship is so important. And again, we'll talk about how we make that work. So because I'm able to replace the entire left side and re-express it as the product rule of u and y, that means over here on the other side, you really just have a function of x, right? Multiplying u times q, it's all just one big function of x. But what we can do now is we can integrate both sides. So I can integrate this side, so I'll sneak a little dx in here. We can integrate this side, and this is where we really get to be able to solve. So what happens then is here on the left side, obviously we're taking the integral of the derivative. Those are inverse operations, they cancel out. So the left side simply becomes whatever u of x times y is. And then over here, of course, we'll just, do the antiderivative. So we'll find whatever the antiderivative of, u of the x, times q of x is, right? So I'm just gonna leave that there to say that is what it is. And then our last step then is to simply solve, right? So we can basically take our y and, get it by itself. So we can divide this, u of x over here. So the whole idea is almost like a substitution, right? We're going to have this choice of u. We're going to put it right in here, which allows us to rewrite it as u prime. And again, we're going to recognize this as being the product rule. Integrating both sides now allows us to get y by itself by then dividing by that u of x. Now, obviously, to make all this work, we have to understand what is this choice of u. We have to come up with a method to figure that out. So let's just figure out what this ought to be. And what I'm going to do is work off this relationship here to give us a strategy or a way to calculate what value could I use for u of x that would make this true, and therefore let that process that I just talked about work. So what I'm going to do is I'm going to take this equation, and we're going to solve it for p of x. And the reason I want to do that is I'm trying to come up with some way to give me a way to figure out exactly what u of x is. And I can do that if I divide by u of x, because on the right side here, we get u prime over u. Okay, so again, I'm just taking this relationship and solving for p. Why this is a good idea, of course, is that this right here, u of x in the denominator, and of course this derivative on top, this is the derivative of the natural log of u of x, right? Because remember, when you do the derivative of a logarithm, you copy the stuff on the inside, take its derivative on the outside. So I can actually rewrite this as, whatever this p of x is, to be the derivative of the natural logarithm of the u of x. Now, the reason this is helpful is this is going to give me some things where I can move around and solve. So now what I'm going to do is I'm going to go ahead now and integrate both sides. So I'll sneak a little dx in here. We'll integrate this side. And very similar to how we kind of had that general idea before, over here on the right side, the derivative and the integral, obviously being inverse operations, are going to cancel out. So over here, I'm going to be basically left with this natural log of, the u of x here. So we got that. And then, of course, over here, we're just going to have p of x. Now, I should say whatever the antiderivative of that is, right? So I'm just going to go ahead and keep this as the integral, right? Now, the thing is, we know what that may be. We're still going to have some sort of c value over here. So we're going to do that. And that's going to happen, obviously, as we do our work. But what's important to understand is, as we work this stuff out, we want to now try to get u by itself. That's going to be our goal. So if I solve for u, I can literally take, the natural logarithm with base e and say I can take e, raise to stuff, and then get u by itself. Now, before I do that, I'm going to take my c value and move it over here. So I'm going to subtract it. So I'm going to basically have the antiderivative of p of x dx, and I'm going to move that c value over. I'll call c sub 2 because it's going to be a different number. And we can actually call it plus. I have no idea whether it's positive or negative. But over here, of course, being the natural log of u of x, now I can finally do something where I can solve for u of x in a way to calculate involving p. So what I'm going to do is I'm going to say, of course, when we rewrite this, e raised to all this stuff is going to be equal to the u of x. So I can say that my u of x is going to equal e, and again, we're going to raise that to all the stuff on the left side there. So the integral of p of x dx, and then, of course, plus that c value. Now, just like we've done before with growth and decay, when we do that sort of thing, we can definitely take that c value and put it in front, right? So we can make this ce raised to the integral. But one nice thing that I will say is going to be true about this is that whenever we choose to be our u, if you remember from previous, right, we took that u and we put it on both sides of the equation. And because we're going to place the u on both sides of this equation, we actually don't need to keep this c here, because c technically would be multiplied to both sides of the equation, and you could easily divide that out when you simplify. So when we talk about what is this choice of u that we're going to have, well, the choice of u is going to be whatever e raised to the integral of px dx. And this right here is the magic. This is how we figure out what is that special u value that we're going to multiply to each part of this standard form differential equation, right? We're going to figure out so we're going to figure it out by taking the integral of p of x dx and raising e to that value. So let's talk about putting this all together. Step number one, obviously, make sure you're in standard form. Okay, sometimes they may not be written that way, so you want to make sure you have your derivative plus some function of x times y equals a function of x. Then you got to figure out what is this u value you want to put in here, right, to make the substitution work. So you calculate that by taking e raised to the integral of the p of x dx. So whatever that expression, or I should say function of x in front of y is, that's what's going to go up here in this integral and exponent. Now, once you figure out and calculate and simplify this part right here, you multiply the entire equation by u of x. So it's going to be multiplied times the dy dx. It's going to be multiplied here in front of u p of x and q of x. And again, we do that because multiplying, especially right here with that u of x, means we can replace that with u prime. And by doing that, we're creating a product rule. And once we have that product rule written there, we can rewrite it that way. And like we demonstrated before, we'll integrate both sides. And that way we'll actually be able to get y by itself and have an answer. Okay, so let's try this out. Now, first off, when you look at this example, it's not initially looking like the way I wanted to, because again, I don't have the derivative minus or plus, doesn't really matter, a function of x times y and then a function of x. I don't need this x here. That's really the big problem. I need the derivative by itself. So my first step is, first off, I'm going to rewrite y prime to be dy dx, just so it looks a little bit more like what I defined it. And then to get rid of that x, I'm going to divide everything by x. So if I divide the next term by x, we can say this is 2x to the negative first times y. And then if I divide this side by x, it becomes x to the first. Okay, so by dividing all the terms, both sides of the equation, by x, I can make it look like standard form because I have the derivative. Here's a function of x times y and an x. Now I should note the negative does go with this function. So when we talk about what p of x is, it's negative 2x to the negative first. So the next step, obviously, now that I have it in standard form, is I need to calculate what this u is going to be. So remember, to calculate my u that I'm going to be placing in there, we're going to raise e to the integral of the function here in front of y. So this is negative 2 times x negative first. And actually, just to help us integrate this, I'm going to write this as negative 2 over x instead of negative first power, right, with respect to x. And I'm doing that because obviously now you can see this will be negative 2 times the natural log of the absolute value. So that means the u of x equals e, and the antiderivative is negative 2 times the natural log of the absolute value of x. And again, we don't need to worry about the plus c part. We already talked about that. So we can simplify this even further, obviously, because when you put this power up here, this is basically, e times the natural log of, x to the negative second. And obviously, e raised to the natural log, those are inverse operations. So all of this just works out to be x to the negative second. So now that I've done this calculation, this u value, right, x to the negative second, that's going to be multiplied times each piece here in standard form. Okay, so what I'm going to do now is I'm going to take this x to the negative second and multiply it times my linear differential equation here, first order, in standard form. So this is what overall I'm doing, and I'm going to go ahead and distribute this. And again, notice it's both sides. So when I distribute this, I'm going to get x to the negative second dy dx. Now, when I multiply this times this, remember, we have already an x negative first, so that's going to be 2x to the negative third times y. And then, of course, x times x to the negative second would be x to the negative first. Now, again, this is where we can actually see it happen. We need to recognize this now as being the product rule. And you have to know what the product rule is going to be. So look at what you're multiplying times dy dx. Look at what you're multiplying times y. Those are obviously the things we're shooting for to identify the pieces of the product. So obviously, if we have this expression, this is the same thing as looking at it as the derivative of the product between y and x to the negative second, okay? And I really like to focus mostly on this because obviously dy dx is the derivative of y, so if you want to know what is the other piece in the product rule, it's what you're multiplying that by. That's an easy way to look. And now a check, of course, is this the derivative of that? And that's definitely true, okay? And you can always double check yourself by looking at what's written here and doing the product rule. Now over here on the right side, it's still going to be x negative first, but again, now we have a way to get y by itself. Now the next step obviously is to get rid of this kind of derivative idea. So we're going to integrate this side with respect to x and integrate this side with respect to x. So that means over here on the left side, the integral and the derivative undo one another. So you're simply left with y times x to the negative second. Now on this side, the derivative or the antiderivative of x negative first is, the natural log of the absolute value of x plus our c value. And then once you get this, our very last step now is to solve for y. So to get y by itself, I'm just going to multiply the other side by x squared. So this is going to be x squared times the natural log of the absolute value of x plus, and then this will just be c times x squared. Let's try another example. Now again, this one right here does not look like standard form. So my job is to again get it in standard form, move things around. Now first off, I don't even have a dy dx. So my first step is going to be, all right, let's go ahead. I'll leave this y plus 1 cosine of x dx here, and I'm going to add the dy to the other side. I'm going to do that because now in the next step, I can go ahead and divide that dx over. And I now officially have the derivative of y with respect to x. So you need to get that first. Next, we need to make it look like standard form, okay? So again, looking back at what that is, we need our derivative plus a function of x times y plus some function, right? So that means I got to get, obviously this is all by itself, but we need to go ahead and keep this up with y. So I'm going to take my cosine and distribute this. So if I distribute cosine here, that's going to be y times the cosine of x, and then times 1, of course, gives me cosine x. So to make standard form, what I'm going to do is I'm now going to take my y cosine x here and subtract it over here. I'm also going to flip it around just so it looks the way we normally used to it. So dy dx minus my y times cosine of x is going to equal the cosine of x. And again, this is standard form because I have my derivative. I have a function times y. And by the way, that function of x is negative cosine of x. That's why I'm multiplying times y. And this then equals, again, a function of x. So step number 2, let's calculate our u value. So, of course, the u of x that I need to multiply everything by is equal to e raised to the integral of our p of x, right? The function of x that's being multiplied times y. So again, this time it's negative cosine x. So if I put a negative cosine x in here and simplify, here's what it's going to be. The antiderivative, obviously, of negative cosine of x, that's going to be negative sine x. So this means this is e raised to the negative sine of x. And that's pretty much as far as I can simplify it. So that means I'm going to take this u value, right, my e to the negative sine of x, and multiply it times all the pieces here in standard form. So what that looks like then is when I take this and multiply times every one of these pieces in this equation right here, means I'm going to have e to the negative sine of x times my derivative, dy dx. And then we'll subtract from that, obviously, y times the cosine of x, and we're multiplying that times e to the negative sine of x. And then, of course, on the other side, we again have our cosine of x, and we'll multiply that times e to the negative sine of x. I'm going to put a little multiplication symbol in here just so we don't get confused. Now, again, our job is to recognize the product rule, and I like to look here. Clearly, this is the derivative of y, and this is obviously the other thing being multiplied by it. So it looks like y and this would be the things that were being multiplied in the product rule. And that should make sense because the derivative of this is clearly right here. Okay, we have the cosine of x times e to the negative sine of x, so with a minus. So that clearly makes sense. So that means this whole left side is equal to the derivative of the product of y and e to the negative sine of x. Okay, and again, once you write that down, pause and double check the product here is definitely being done as far as this derivative right there. Now, obviously on the other side, we still have our cosine of x, I'm going to use parentheses this time, and then multiply times e to the negative sine x. So let's go ahead and antidifferentiate both sides. So we'll find the antiderivative here with respect to x, and then do the same thing here. As always, over here on the left side, we just get our y e to the negative sine x because those are opposite operations. We don't need the plus c or anything. And then over here, the antiderivative of this is going to be negative e to the negative sine of x. Now, when I figured that out, I should tell you, I kind of see where I'm going with it, but if you need to do a substitution kind of off to the side and work that out, go ahead and do it. Obviously, the substitution would be the negative sine of x, whose derivative is right here. So obviously, this is what I'm differentiating to get there, but I just want to make sure you saw where I got that, okay? So now that we're here, let's solve for y. So that means I'm going to take my e to the negative sine of x and simply divide that over. And by the way, since this exponent is negative, when I divide it over, I'm really just multiplying times e to the negative sine of x. So my answer is going to be y equals negative e to the negative sine of x times e to the positive sine of x, because again, I'm dividing this one over, and then plus c times e to the positive sine of x. And you can simplify that because clearly when you have negative e to the negative sine of x times e to the sine of x, that's just negative 1. Okay, let's try one more. Now this time, as opposed to just solving it, we're going to go one step further and find the particular solution. Okay, so obviously we have a condition here, an ordered pair that we can plug in and then end up solving for what the actual value is going to be. So we're not going to have an answer with C in it. We're going to go ahead and get the final result as the particular solution. So first step obviously is to do the solving by itself. So let's make sure we're in standard form. Now looking at it, here's my derivative. It's not alone, and it's also being multiplied by x. So what I need to do is I need to divide all these things by x, and then I need to move the piece over so I have standard form. So if I divide everything by x, it's going to leave me with the derivative. And again, I like to write it as dy dx. And then it equals x divided by x is just going to be 1, right? And then we have y divided by x. I'm going to call that x negative 1 times y. And then plus 2x to the negative first. Now, to finish standard form, I need to move this term right here over because you want the derivative, and then you want a function of x times y on that side and everything else on the other. So standard form for this one is going to look like dy dx. And then again, subtracting this term over is going to be minus x to the negative first y. And then on the other side, I just have my 1 plus 2x negative first. Next, let's go ahead and calculate our u. Okay, so again, our u here is going to be whatever e raised to the integral of this stuff, right? So this is negative 1 over x dx. Okay, so that's going to be e raised to the negative natural log of the absolute value of x. And of course, you can simplify that to just be x to the negative first. So let's go ahead and take that and multiply it times the entire, standard form. So this right here is going to multiply times every piece in this equation. Okay, so what that does is going to give me my x to the negative first, dy dx. Okay, and then when you multiply, the x negative first times this one, you have a negative 1 and a negative 1. So that's going to give me minus x to the negative second y. And then on the other side, 1 times x negative first is that. And of course, when you take the 2x negative first times that, you get 2x to the negative second. So it looks like this on the left side is the product rule between x to the negative first and y. And again, that makes sense because this right here is the derivative of x to the negative first. So that means that this left side really is the derivative of the product of x to the negative first and y. On the other side, obviously, we'll just keep this as that expression. So I'm going to write equals just x negative first plus 2x negative 2. But again, we're of course going to find the antiderivative of both sides. So let's go ahead and integrate this side with respect to x. And then we'll do the same thing with this side. We'll do all this with respect to x. So obviously, the antiderivative of the product rule is just going to give me that product. And then over here, we're going to get the antiderivative of x to the negative first, which is the natural log of the absolute value of x. And then by power rule, this will be negative 2x to the negative first plus our c value. Now, normally here's where we just solve for y, and I'll go ahead and do that by multiplying the other side by x. So we get x natural log of the absolute value of x minus 2 plus c times x. Now, in the past problems, this is where we stop. But because we have this initial condition up here, we want to go ahead and go one step further and solve for it. Okay, so I'm going to take this information now and plug it in and figure it out. So we know that y is going to be 10 when x is 1, right? So we have 1 times the natural log of 1 minus 2 plus c times 1. Well, the natural log of 1 is 0, right? So this is basically 0 minus 2 plus c, which tells me c is equal to 12. And so our final result then is going to be y equals x times the natural log of the absolute value of x. And then we have our minus 2. And then don't forget, obviously, there's an x with a c there. So this would be plus 12x as our particular solution.